Today we're going to be looking at comparing linear, exponential, and quadratic functions. All right, start here with the state standards. You can see several of these say compare, compare, compare. So make sure you review the state standards. Remember that a linear equation is an equation of a line. This is an example of a parent function of an exponential function. You can see that it increases quickly. If it were exponential decay, it would decrease quickly and approach the x-axis. This is a quadratic function. This is an example of a quadratic function. So it's a U-shaped graph called a parabola. So remember, the shapes of these three types of functions will be important for the lesson today as we compare functions. All right, to be successful today, you need to be able to determine whether data can be represented by a linear, exponential, or quadratic function. You need to be able to write functions to model data, and you need to be able to compare functions using average rate of change. All right, and the vocabulary term for today, average rate of change. If you remember, average rate of change is your change in y's over your change in x's. They also write it as f of b minus f of a. This is your two y values over b minus a. So they're just looking at these as ordered pairs. If you have two ordered pairs, 2 points on a graph, you can find the average rate of change by doing the change in y's over the change in x's. All right, you can do the same thing with linear, quadratic, and exponential functions. All right, a couple key ideas here. Make sure you are aware of these. Linear function, the first difference are constant, so we're going to be looking at this a little bit later today. Exponential functions, consecutive y values have a common ratio. And a quadratic function, the second difference are constant. So make sure you review these key ideas, have these in your notes, and refer to them if you have a question. Very quickly, the second key idea here, comparing functions using the average rate of change. It's important to know as a and b increase, the average rate of change between x equals a and x equals b of an increasing exponential function, f of x, will eventually exceed the average rate of change for an increasing quadratic function, g of x, and an increasing function, h of x. Increasing linear function, h of x. So as x increases, f of x will eventually exceed g of x and h of x. So basically what that says, if you are looking and comparing functions of a linear, quadratic, and exponential function, if you expand the graph far enough, the exponential function is going to increase faster than linear or quadratic. All right, the second one says as a and b increase, the average rate of change between x equals a and x equals b of an increasing quadratic function, g of x, will eventually exceed the average rate of change between x equals a and x equals b of an increasing linear function, h of x. So as x increases, g of x will eventually exceed h of x. So very similar. This says if you are comparing a linear and a quadratic function, if you look at it, the quadratic function is going to increase eventually, maybe not at first, but eventually the quadratic function will increase faster than the linear. All right, using graphs to identify functions. Example 1, plot the points. Tell whether the points appear to represent a linear, an exponential, or a quadratic function. All right, so we've got 3 sets of points here, so let's graph these points. All right, so for the first one, we have 4, 4. So 1, 2, 3, 4. 1, 2, 3, 4. So let's put a point here. 2, 0. And then 0, 0. And then I've got 1 and negative 1/2. Didn't quite get a half, but kind of hard to get those points exactly. But let's see what we look like. Negative 2 up 4. All right, so if you look at this, this looks like a quadratic function, a U-shaped graph. So in my opinion, this is going to be a quadratic function for A part. Let's look at B. B is 0, 1. 2, 4. And then 4, 7. And then negative 2, negative 2. And then negative 4, negative 5. All right, in my opinion, just looking at these points on this graph, that looks like a straight line. A straight line is going to represent a linear equation. All right, C part, 0, 2, 2, 8, I've got 1, 4, and I've got negative 1, 1, and I've got negative 2 and 1/2. All right, so this looks like an exponential growth function. So if we want to label these, we could say the first one, let's say A part would be quadratic. The second one looks like a line, so it's going to be linear. And the last one looks like exponential growth. All right, so I erased my handwriting there that was hard to read, and I typed that out. So again, A part, a U-shaped graph, which is a parabola, that is a quadratic. B part, a straight line, linear function, and C part, an exponential growth function. Example 2, using differences or ratios to identify functions. Tell whether each table of values represents a linear, an exponential, or a quadratic function. If you look to the right side, you see a couple study tips here. Linear functions have a constant rate of change. So for equally spaced x values, the differences of consecutive y values are constant. Exponential and quadratic functions do not have a constant rate of change. All right, so if you look at A part, you can see that your x values increase by 1. So I can say there is a constant rate of change between my x values here. And here I have constant rate of change as well. So the x values are not really what we're going to have to look at. This is, for all of these, the constant rate of change between your x values are the same. So what this is really talking about is we're looking at the y values. It says the differences of consecutive y values are constant. So if it's linear, the y values are also constant. All right. And the second study tip says first determine that the differences of consecutive x values are constant. So we did that for all three of these. Then check whether the first differences are constant or if their consecutive y values have a common ratio. If neither of these is true, then check whether the second differences are constant. If the second difference is constant, remember that means it's quadratic, not linear. All right, so let's look at these. So for A part, to go from 11 to 8, I'm going to minus 3. From 8 to 5, I subtract 3. 5 to 2, subtract 3. And 2 to negative 1, I subtract 3. So that is considered a constant rate of change. So if I have a constant rate of change with consecutive y values, that means it is a linear function. So for A part, I can say that is linear. All right, so let's look at B part. B part, I'm looking at the y values. I've already determined that the x values increase by 1. So the y values go from 1 to 2. That's an increase of 1. Then it's an increase of 2 and an increase of 4. So look at the pattern. How do you get from one term to the next term? You can see that you can multiply here 1 times 2, if I multiply by 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So this one now has a constant ratio. So if it has a constant ratio, you're looking at something besides a linear. So this is going to be an exponential function. All right, let's look at C part. So again, we've already determined that the X values are constant. They increase by 1. Now we're going to look at the Y values. So we go from -1 to -2. That's an increase of, or a decrease, I should say, of -1. So this goes down by 1. All right, the -2 to -1 is an increase of 1. -1 to 2 is an increase of 3. And 2 to 7 is an increase of 5. All right, so that is definitely not consistent. So that doesn't have a constant difference for your first one. And it also doesn't have a common ratio. All right, so there's no common ratio. There's no number you can multiply to get from one term to the next that is the same number for each time. Like up here, we multiplied by 2 each time to get to the next term. All right, so remember it says check whether the second differences are constant. So now we're going to check the difference between -1 and 1, 1 and 3, and 3 and 5. This is called your second difference. All right, if your second difference are constant, then it means we have quadratic because it would be your second degree. So from -1 to +1, I have to increase by 2. From 1 to 3, I increase by 2. Look at that. And from 3 to 5, I increase by 2. So that means my second difference are constant. So this table represents a quadratic function. All right, so hopefully you can look at the table and you can determine whether it's linear, quadratic, or exponential by comparing the Y values. You do need to have a constant rate of change in your X values, but the Y values is really going to determine whether it's linear, quadratic, or exponential.